So the last topic in the course is divergence theorem, and this is the third major integration theorem that we have. So we've already learned about Green's theorem and Stokes' theorem, and let's just go over briefly the premise of those. So the premise of Green's theorem was that line integrals are hard, and you could change those into the integral of a region in two-dimensional space. The premise of Stokes' theorem was that surface integrals of vector fields are hard, and you could change those into a line integral along the boundary, and possibly living in three-dimensional space. The downfall of Stokes' theorem is that it only talks about the integral over the curl of a vector field of a surface, over a surface. So if you have just any general vector field that you want to integrate over a surface, Stokes' theorem might not help you. So that's where the divergence theorem comes in. So Stokes' theorem was able to change the integral of a curl over a surface to a line integral. Divergence theorem can't change it into a line integral, but okay, we're going to come up with the formal statement in a minute. It's if a bunch of conditions, just like everything else in this course, but I'll write the then so that we know what we're doing. So integral of any vector field now over a surface is going to be equal to the triple integral of E is going to be the thing inside the surface. So it has to be a closed surface, meaning we can't do half a sphere anymore. We have to integrate the whole sphere because it has to be the region E basically is closed inside, and then S is the surface of the sphere. That's a terrible picture, but hopefully you get the idea. We're also going to write out the conditions. So basically conditions say everything's nice. So if E is bounded meaning there's nothing going off to infinity. So for example, you couldn't do the first octant or something as a region. It has to be bounded. Closed meaning like closed open sets. That was if you could draw a ball around every point and still have it be in the set. That was open, so closed is the opposite. And then piecewise, smooth boundary, where the boundary of E equals S. So S is the surface, and E is inside. And then we also need some conditions on F. So F has to have continuous partial derivatives. I'm going to write on and around E. And what that just means is that if you have some region E in three-dimensional space, let's try to make this look three-dimensional. You don't want F to be nice inside E and then nice like on the surface of E and then really ugly right outside E. We want to have some leeway. So we want like a little bit bigger than E. It doesn't have to be much bigger at all. F is nice on a region of three-dimensional space a little bit bigger than E. Sometimes the technical term you'll see if you ever take analysis or just read any serious math book, on a neighborhood of E is what people will say. And that just guarantees that the calculus doesn't get really ugly or really wrong. We just want to make sure the statement of the theorem is true. So, okay, as long as everything is nice, that's what up here says, then you can turn a surface integral of now any vector field, doesn't have to be the curl of another vector field, into a triple integral over a region. And the nice thing about div, if you've noticed maybe when you're calculating gradient curl in div is the nicest one. Div makes everything simple. So some uses of this. For example, sometimes div of f is 0. Sometimes f is a pretty complicated thing, but when you calculate the div, it's 0. I can even make an example of this right now. I can make something where the div of f is 0. Let's call it like x squared negative 2 xy plus y comma negative z. Right? Then if I calculate div f Then I get 2x, that's the partial with respect to x of the first component. Partial with respect to y of the second component is minus 2x plus 1. Partial with respect to z of the third component is minus 1. So that all cancels out, and that's 0. So if I said find the surface integral of that vector field over a sphere even, which is not too bad of a region, that might be hard. But because div f is 0, now it's easy. Okay, so that's one nice use, because then you can easily say the surface integral is 0. Another nice use is if you have lots of pieces to S. Like a sphere isn't so bad, you can parameterize it all at once, but like let's say you had a cylinder. It's not terrible, but you have to do the top, bottom, and then this round piece in 3 separate integrals. Whereas if you changed it to a triple integral, you're integrating inside the volume of a cylinder. Well, we've been able to do that in 1 integral. So that might be nicer. And there's a cute example, actually on Wikipedia, that we'll see of the third one, which is just integral over E is easier. It might seem like it could be harder, and it can be, since it's a triple integral. But sometimes the surface integrals over vector fields are really hard. So might be easier.